Hi, and welcome to Book Club. This is actually book club number 8. And what we do at Book Club is get an amazing textbook like this, Aircraft Engine Design. And dear reader, this is all about you teaching yourself. The power of self-learning. These books are well written. They've got a ton of figures, good equations. It's a tremendous resource. All you got to do is dig. So I'm your guide through the reading process, and all I'm going to do is just hit the wave tops, hit a couple of key concepts, keep you excited, and keep you interested, and the rest is up to you. And so this textbook is one of my favorites. So all about aircraft engine design. This is taking in air and using whatever fuel you're carrying it to make propulsive power. Now, in the last one, we were actually digging into rocket engines. A little bit more of my expertise. I spent some time here as faculty doing jet engine heat transfer, so I'm fairly familiar with the inner workings of the jet engine and things like that. But what you'll find if you paid attention to that rocket engine one is there's enough sort of, I'll say, introductory concepts that throughout that whole book that it really feels like an introductory concept. This is not going to feel like an introductory concept. This is going to feel like let's get down to business, which is great. In fact, throughout the book, there's this thread where they basically take a design concept for an advanced aircraft fighter, and every section in the book is basically walking it through. And so this book is really written from a systems engineering point of view all the way down to the components. And that's how it's organized, and that's how it's going to feel, okay? And as such, the opening lines of the book, it's going to talk about a couple prereqs. So, if you haven't had some sort of aircraft design, then you really ought to go take a look at it. Now, Kuchuman's my favorite book. That was actually book club number 1. So you can go take a look at that one if you want. Raymer is a fantastic text. Go have some sort of basis for aircraft design, because basically this is going to open up from a starting chapter with a little bit of overlap of a reminder. Here's the goal of the engine is to serve this aircraft. Okay, that's sort of step 1. The second one is you really need to have some basics of propulsion, and I cover some of this, of course, in the rocket engine one. I'll do a decent job here covering some of the basics. And then ultimately, in my thermal fluids one, which is really sort of the third prereq, is thermo. Okay, this book is not going to get into the thermodynamics of temperatures and pressures and isentropic and all that. It's going to use it heavily. So if you haven't had thermodynamics, again, you can go take a look at my book club. That was actually the quad set of books, book club 2 to 5, where I absolutely tie all of that in together with fluid mechanics and thermodynamics. Okay, so those are the prereqs. And the story arc, like I said, is sort of, there's this advanced air fighter, and we're trying to make the engine for it. And the power of aircraft propulsion is you don't have to carry your oxidizer. Okay, most of the work I've done recently in my life has been with rocket engines, including with Venus on the rotating detonation engine, where you're carrying your own oxidizer. Now, there's all sorts of performance benefits you get from it, but the drawback is that propellant, the weight of the propellant you got to carry. Okay? And so versus Mach number, and this is altitude. I know we got real close to the edge here. I'll just say altitude. There is a regime, okay, usually sort of fairly well boxed by that. And what's happening here in this flight regime for your aircraft is a couple of things. So one, this is an altitude limit. That's color showing up. The orange altitude limit. Your air-breathing engine is going to have a hard time at real high altitudes. Okay, not enough air for the combustion process, or the air density is too weak for whatever your compression system is. However you want to think about it, there's effectively a top altitude that's not going to happen. Okay, on the left, this is stall. So it's your aircraft can't have enough lift between the wing pressure is related to density and your speed squared. And so it's not enough to keep the aircraft in the sky, so you're going to stall. No, it's going to happen for different aircraft. This line is not set. Absolutely, if you're a glider, it's going to be very, very different than if you're a fighter jet. Okay, this one below here is your structural limit. And so as you go fast, for that same reason, that rho v squared, if you're staying low where the air is dense and you pick up a ton of speed, at some point that air pressure against your vehicle is going to be too much for the structure. And so that's a structural limit. And then usually around, this is set generically as your temperature limit, as a box. Now, as a person who does hypersonics, it's not just a box. It's a decent approximation for what most aircraft are going to do, but at high speeds, it takes a little bit more shape than this. So it's not just a flat line at a Mach number. But you can imagine that this will be good enough for sort of our purposes here. We're not going to get into hypersonic air breathing. That's not the goal of this book. And so that's your basic limits of this. Okay, and so a couple things we want to talk about from a normalization point of view. Throughout the book, you're going to see, unfortunately, you're going to see nomenclature vary like from chapter to chapter. That's just the way it works. At the aircraft design level, they're going to have some nomenclature. They're going to use things like some alphas and betas, and then when we get into the engine, alpha and beta is going to mean something very, very different. Okay, so unfortunately, that's the way it goes. But there's the total temperature, which is the temperature of the air, and then it's 1 plus, you get gamma over minus 1 over 2 Mach squared. I did derive this in the thermal fluids one. This is basically isotropic compression. So total temperature, this is as that air is slowed down, no matter how it's slowed down, it gets hot. If it's slowed down isotropically, this is the temperature that you get. Okay, that's a gamma minus 1. A reminder, gamma is the ratio of specific heats. So that's Cp over Cv. For air, this is about 1.4, and so we pick up. Actually, in fact, in thermal fluids, that derives why it's this gamma minus 1 squared for 2. All right, that's total temperature. And so one of the variables you're going to see a lot is theta 0, which is the current total temperature divided by the temperature at standard pressure and temperature. Now, standard pressure and temperature is just sea level, 14.7 psi, absolute, 101,325 pascals, and then the standard temperature, right? So, PT, relatedly, is total pressure, and you still get this 1 plus gamma minus 1 over 2 Mach squared, and this gets raised to the gamma over gamma minus 1. Again, it's isotropic. Go take a look at those derivations in the previous class. And the related symbol is a delta 0, almost a little too low, okay? And that is also P total over P standard. All right, so theta and delta, which is most unfortunate, right? If you go look in that thermal fluids class, what you're going to see, theta referred to as a momentum ratio, and delta is a mass ratio. Those are boundary layer terms. Okay, again, the point of engineering is communication, and usually within a field, people are consistent. Unfortunately, if you kind of hop at a systems level, you're going to be hopping between fields, and so really just make sure it's clear to people when you're using symbols like that what you talk about. Don't be that jerk in the room that's sort of stuffing your nose up because people don't remember what theta is. Okay, you don't be that person. All right, and then just for a reference, okay, the other we talk about all this stuff. Dynamic pressure, which is normally labeled as Q, so that is 1/2 rho v squared, and if you convert this, that's a gamma over 2 pressure times Mach squared. Okay, same thing. If you take an idea of Q divided by the standard pressure, this is usually on the realm of 0.1 to 0.2 for commercial, and 0.2 to 0.4 for fighters. Fighters, commercial aircraft. And we're going to see why. But basically, fighter, the engine is going to be smaller. You're going to get a lot more thrust out of it, and your wings are going to be shorter as a result. And so we'll end up seeing where all this comes from. Okay, but this is I showed this, of course, in the Kuchman book, where you go derive kind of thrust loading versus wing loading. Again, thrust is thrust the engine. This is what we're developing divided by the weight of the aircraft at takeoff, and wing loading is the weight of the aircraft divided by the area of the wings. And so, we went and derived all of the equations that sort of form, but this is going to form all of the design points. Just again, as a reminder, sort of that the pull from aircraft design this is one of those key ones where you have climb constraints, you have turning constraints, you have takeoff, you have landing, And so here are your optimal design points. And basically, anything in this area is going to be okay. And so I wanted to show you, I kind of overrode it a little bit. This is sort of historical thrust to weights versus wing loadings. And so you can Google this. There are a ton of these out there flowing around the aircraft. But for an example, this is the F-15E. So that's a pretty high thrust to weight and wing loading. Again, most supersonic aircraft are actually going to have thrust to weights that are going to be in that greater than 1 point of view. Okay, it just works out that if you need enough thrust to get to the sound barrier, it's basically the same as saying at takeoff I can, point vertical. And so, if you ever been to an air show, it's the requirement was not be able to immediately turn vertical and climb. It's the requirement was to get supersonic. It just so happens to size that engine for that. Okay, some other interesting ones. Here's the F-14 over here, so a little bit lower thrust to weight and a little bit larger wings. Now, why is that? They have the swing wing, so they're able to get through the sound barrier a little bit easier. Right? That's we talked about that in the other class. Some other ones. There's some MiGs, Mirage, F-100, F-5. So you see sort of a broad range of aircraft and configurations. I was looking for if there's any commercial ones on here. There's not. Okay, so this is all sort of military aircraft. So you can go look online and find some good examples. Oh, and that didn't load, but we'll start talking about that one on the next class. So that's the conclusion. We'll go back to the book here. It's a great book. Come dive in with me. And really, I always say read the book, but you got to read the book on these examples. This is actually the biggest joy of this aircraft, of this book, is because it starts and it's building a real aircraft, and the thread throughout is absolutely tremendous. And you'll see how it ties in. Again, this is from books that I've done before, especially considered like the rocket science book. This is I'd say a deeper dive, and not like that it's harder. It's actually a more complete dive, because in the end, right, when you're designing an engine, it's all going to be tied towards aircraft, and you're going to see what is really in these chapters are trade spaces that we didn't do any of the real trade space in that rocket book club. I might have talked about it, but we didn't actually get into the trade spaces of here's how you would choose let's choose this pump size and let's choose this thrust chamber size. We didn't get into the trades. We sort of were able to stay at the engineering. This book is actually all about the trades, and so it's what makes this really, really great book. So come join with me, read along, and remember, this is your learning. Take advantage of it. And you don't need some professor. You don't need any of that stuff. Just grab a great book, and let's go. See you next time.